Okay, in this question, it looks like we've got these two substances called yellow and purple and in a thermally insulated container, so we should assume it's a closed system. And their initial states are marked on these diagrams. So we don't really have any given numerical values, but we do have these graphs that I think are going to tell us everything we need to know. Because as these are combined, and I think the question is we want to figure out what's the final state. In other words, what temperature does everything end up at as a final equilibrium temperature, and what state, what phase is everything in? So it looks like to begin with, how would you interpret what's going on like right now? At this instant, what do we have? What are we looking at here? We've got yellow in what state? Yeah, it looks like we've got solid yellow at, and what's the initial temperature? Yeah, 50. And it's degrees Celsius. And by the way, if we needed to, we could figure out the heat capacity of this substance. Because how is heat capacity defined? What is heat, when we talk about the heat capacity of a substance, what does that mean? Yeah, well, it's measured in units of joules per Kelvin. So that's measuring what sort of thing? What is joules measuring? What is kelvins measuring? It does work out to be related to the slope on this graph, but what sort of, like if you measure joules, what are you really measuring? Yeah, energy and temperature. Heat capacity is just a measure of change in energy over change in temperature. How much the energy change, how much energy it takes divided by how much the temperature changes as a result. More formally, we should really call that heat over temperature. But the situation we're talking about, we're ignoring work, so heat is delta E thermal. So change in energy over change in temperature, how much heat it takes per degree of temperature change. Or per Kelvin, same thing if we're talking about a change. So if you take a look at this line here, delta energy would be the horizontal and delta temperature would be the vertical. So you could take, for instance, it looks like if we go horizontally 1,000 joules forward, we're also going up, and it looks like about 150. So 1,000 joules over 150 Kelvin would tell you the heat capacity. And that is just the inverse of the slope here. However, I don't think we actually need that value in this case because we should be able to do everything just from these graphs. We've got solid yellow at this initial temperature. And also purple is, I'm guessing this is meant to be solid phase. And initial temperature looks like it's somewhere around 525-ish. And then what's going to happen? If we've got this cold solid yellow and hot solid purple, which way is energy going to flow? Yeah, heat flows from purple to yellow because heat's going to flow from hot to cold. So the yellow is going to be gaining energy and the purple is going to be losing energy. So if we mark that on the graph, we know yellow is going to be gaining energy, purple is going to be losing energy. And we should assume, since presumably there's no weird supercooling or superheating going on, we should assume these stay on the graphs. So yellow gains energy as purple loses energy. And what should we assume about the amount of energy yellow gains and the amount of energy purple loses? They should be the same amount, yeah, because this is a closed system. So if yellow gains, let's say 100 joules, that's because purple is losing the same 100 joules. So what we can do is we can take this on the graph one step at a time by looking at equal increments of energy. We can say purple loses a certain amount of energy while yellow gains the same amount of energy one step at a time. And we can look at this in terms of getting to the next transition. For instance, if we take a look at yellow going up to the phase change. How much energy does that take? Just based on the graph. Yeah, that looks like 1,000. If we take a look at the starting value compared to the ending value, that's 2 tick marks on the graph, and it looks like each tick mark is 500. So this is plus 1,000. So we are gaining plus 1,000 joules. And at the same time, purple has to lose 1,000 joules. So let's go 1,000 joules to the left. That is 2 tick marks to the left. 2 tick marks to the left here. Let me actually use smaller arrows there. I think that's going to be so we know yellow gains, let's say 1,000 joules. And of course, it's probably going to gain more than that. But let's start with 1,000 joules gained for yellow and 1,000 joules lost for purple. And are they now at the same temperature? No, we haven't reached the same temperature yet. Yellow is currently at 200 and purple is at maybe 460 or something. Since they're not at the same temperature yet, temperature or heat is going to continue to flow. Yellow is going to continue to gain energy. Purple is going to continue to lose energy. Let's try just going forward in 1,000 joule increments. Yellow gains 1,000 joules. Purple loses 1,000 joules. Are they now at the same temperature? If we've got, looks like yellow is still at 200 because it's going through a phase change. Purple is now at a little under 450. So still nowhere near the same temperature. So let's keep going. Yellow gains another 1,000 joules. Purple loses another 1,000 joules. Have they reached the same temperature yet? Not yet, so we keep going. Yellow gains another 1,000 joules, and I would keep going in a nice, neat, easy number to use, maybe just keep going by 1,000 joules each step until they get really close, and then maybe look at smaller numbers. So yellow gains another 1,000 joules, purple loses another 1,000 joules, and it looks like purple is now at 340-ish, so they're still nowhere near the same temperature. So let's go another 1,000 joules. Actually, maybe we should go another 100 joules at the moment, because 100 joules will take us to the end of this phase change. So 100 or 500. 500 joules for yellow, 500 joules lost for purple. We're still doing equal increments, same increments of energy change. And now yellow is all liquid at 200 and purple is at 300. So we're still going to go through more energy transfer. But at this point, we got to be careful. We might want to go by just 500, just a single tick mark at a time. So let's say yellow gains 500, purple loses 500 joules of energy. Are they now at the same temperature? Not yet, right? We're at, it looks like yellow is at a little below 250 and purple is a little above 250. So not quite yet. Let's go one more tick mark and see what happens. Yellow gains 500 joules, purple loses 500 joules. And now what do you see about the temperatures? Yeah, they have reached the same temperature. So by exchanging the same amount of energy, they have both reached 250 degrees Celsius. And if they're at the same temperature, that means, what does that tell you about heat flow? This is equilibrium, right? Heat only flows because there's a difference in temperature. If everything has reached the same temperature, there's no more reason for heat to flow, so nothing more happens. This is the final state of the system, if we wait long enough. So it looks like the final state, once all the heat that's going to flow has finished flowing, then they've all reached the same temperature. Yellow is now liquid, all liquid at 250 degrees, and purple is still solid, also at 250 degrees. So that would be the final equilibrium state of the system. assuming we wait long enough for that to happen. Yeah, no, I mean, no explicit written equations needed. Informally, the equation we've been using is that delta E thermal, or delta E for the yellow plus delta E for the purple equals 0. So we are foundationally basing this on the idea of conservation of energy, that the changes in energy balance out. One of them gains a certain amount of energy, the other one loses the same amount of energy. But we don't really need to use that equation beyond that because we can get all the information we need from the graphs. We can look at if yellow gains this amount of energy, what does it look like now? And yeah, I think for the answer, I would just write down the final temperature and final phase of each substance. So I would say the final situation is we have all liquid yellow at T final equals 250 degrees Celsius. And purple, of course, is still solid because it didn't go through any phase changes. And also a final temperature of 250 degrees Celsius. So that's how I would describe the final situation. And if you want, you could also draw out an energy interaction diagram. You could say that yellow is gaining thermal energy as a solid, gaining bond energy during this transition, and also gaining thermal energy as a liquid. So that would be 3 bubbles for yellow. And then purple is losing thermal energy as a solid. And so if you wanted to write that out as an equation, that would be delta E thermal for solid yellow plus delta E bond for yellow melting plus delta E thermal for liquid yellow plus delta E thermal for solid purple. And then those all add up to 0 because those are all the changes that are taking place. Any questions on that? All right, let's take a look at one of the other problems then. Can you see question 2 here? Yeah, a lot of these look really complicated on the surface, but then once you break them down into smaller pieces, the smaller pieces are often much easier to understand. The tricky part is being able to put all those pieces together. Let me see if I can get this to work right. Is this now visible? No? What's wrong with this? There we go. Okay. So here, question 2, let me zoom in on that a little bit. We've got 2 substances placed in an insulated container, eventually reach thermal equilibrium. And we have the initial and final states of substance A. So this one's a little different. It shows us a full graph for substance A, and not only shows us initial, but also shows us final. And we know substance B, we don't really have a chart for substance B, but we know its initial temperature is 100. We know it does not undergo a phase change, and we want to know the heat capacity. So again, let's go back to the definition of heat capacity. In fact, in general, if you're not sure where to start, it's often a good idea to just look through the problem, figure out what's actually being asked. In this case, we want to know the heat capacity of B. And it's often helpful to just try writing out either the definition of that thing you're trying to find or some other equations that that quantity appears in. Like, once again, what's the definition of heat capacity? Yeah, energy over temperature, or more specifically, change in energy over change in temperature. And again, formally, that should really be heat over change in temperature, but we're assuming all the transfers here are heat, no work involved here, just heat. So if we can figure out how much energy B absorbs, because it looks like A is losing energy, so presumably B is going to be gaining energy. If we can figure out how much energy B absorbs and how much B's temperature changes, how much energy B absorbs, and delta T, how much B's temperature changes, then we can just divide those and we're done. And we know the starting temperature of B T initial is 100 degrees Celsius. So if we can figure out the T final for B, then we have delta T. Any thoughts on how we could figure out what B's final temperature is? Yeah, we can look at A's final temperature. And how do we know they're going to be the same? Yeah, this specifically tells us that they eventually reach thermal equilibrium. Thermal equilibrium means everything has finally reached the same temperature. So we know that A and B have the same final temperature, which looks like halfway between 100 and 150, so that'd be 125. So we know T final for B is 125 degrees Celsius, same as A's final temperature, because it reaches thermal equilibrium. So that means we're good for delta T. We know the initial temperature of B because that's given. We know the final temperature of B because it should reach the same final temperature as A. We also know there's no phase change, so all of that delta E is just delta E thermal. So we now know delta temperature for B is, it's going from 100 to 125, so that would be plus 25. And since it's a delta, it doesn't really matter if we call that Celsius or Kelvin. So let's just call that 25 kelvins. B gains 25 kelvins of temperature during this process. So we know delta temperature for B. Any questions on that so far? And what else do we still need to know in order to calculate heat capacity? Yeah, we need to know the change in energy. And what do we know about the change in energy for substance B? Right, it's got to be the same as the change in energy for substance A. And this again goes back to conservation of energy. The fact that this is and I think really the thing to look for here is this is an insulated container. This is a closed system. Insulated container suggests this is a closed system. These substances are only interacting with each other. There's nothing suggesting any heat is entering or leaving. So we know that the change in energy for A, the total of all the changes in energy, so all these changes for A, plus the change in energy for B, those all have to add up to 0. So if we can figure out how much energy A is losing, that'll be a negative value for delta E, then B has to gain the same amount of energy as a positive. In fact, we could even solve for that and just say, by subtracting EA from both sides, change in energy for B is the opposite of change in energy for A. And we can do that just by taking a look at the starting and ending values. It looks like A starts at halfway between 7,500 and 9,000, so that's 8,250, I think, and ends at 3,000. So if we want to know the change in energy, we can say delta energy for A is just final minus initial, 3,000 minus, I think that is 8,250, right? Halfway between those. So 3,000 minus 8,250 joules equals negative 5,250. So that means during this process, substance A is losing 5,250 joules. What does that tell you about B? Yeah, B gains that much energy. If you want to write that mathematically, we can say delta energy for B is negative 5,250 joules. The negatives cancel out. We get 5,250 joules. So we know delta E for B, the energy that B gains is positive 5,250 joules. And at this point, we should be able to just divide because we are going back to the definition of heat capacity. Heat capacity is delta energy over delta temperature. So just filling that in, we've got delta energy, 5,250 joules, divided by delta temperature, 25 kelvins. And that should tell us the heat capacity. I think that's, is that just 60? No, that doesn't make sense. 25, 21, so 210, I think. So that would be the heat capacity, 210 joules per Kelvin, just by dividing how much energy B gains divided by how much B's temperature changes. So this really all goes back to the definition of heat capacity combined with knowing that the changes have to be equal and opposite since there's only two changes and they add up to 0, and being able to interpret the graph. So this is bringing together a lot of individual pieces. But I think, again, if you can break that up into those little individual bite-sized pieces, each one of those pieces is pretty straightforward to understand. And once you've got all of them, it's just a question of putting them all together. Any other questions on that one so far? And yeah, I find it is very clear once it's broken down. It's just that it's often difficult to break it down like that. So if you're not sure, again, I would recommend skim through the problem, look for what's the question it's actually asking. So skim through the problem, look for like the very first time it actually asks a question. What's the heat capacity of substance B? Then go back and look through the rest of the problem. Or before you even do that, what's the heat capacity of substance B? Write out the definition of heat capacity or any other formulas that it fits into. And then go back through the whole problem and look through the problem, look for information that would be relevant to that. And you don't have to feel dumb about this. This is difficult stuff. But as long as you can break it down into smaller pieces, I mean, that's really the heart of all math and science, I think, being able to break down a complicated problem into simpler pieces that you already know how to solve, and then putting that all together. Also, I find it can often be helpful if you're not sure where to start, make a list of everything you know and make a list of everything you're trying to find. See if you have any formulas that link those lists together or any formulas, facts, graphs, models, whatever. If you don't, try working forward from what you know and backward from what you're trying to find. Like say, from this stuff that I know, what can I figure out? Or this stuff that I'm trying to find, what else could I figure it out from? What stuff, if I knew it, could immediately tell me the answer? And then keep working your way inwards until those paths meet. If you can figure out, from what I know, I can figure out this stuff, and from that I can figure out this stuff, and from that I can figure out the answer, then that's a path leading from what you know to what you're trying to find. So try that branching out approach. See if you can make an outline for yourself of how to solve the problem. That's often a good way to look at it. Any other questions on that one? Yeah, I'm recording this. I will post it on YouTube afterwards. And yeah, let's take a look at problem 1 since some people were asking for that as well. And then we might be able to take a look at FNT5 as well. We have until 2 o'clock. Let me see if I can pull up problem 1. Is that visible? Okay. Substance called green has a heat of vaporization of 90 joules per kilogram. And again, let's take a look through this and see what is it actually asking. Blah, 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 some extra information. If we remove 450 joules, how much green remains in the gas phase? So we want to know how much of it is still gas. And going back through that, knowing that we want to find out how much is still gas, we know we start with 12 kilograms of gas and we are removing some energy. So let's look at this in terms of initial and final. initial situation, we have 12 kilograms of green in gas form, and it says it's at the boiling point. And it might help to think about this in terms of the three-phase model, given that we're talking about this substance and we're adding or removing some energy. So if you look at this in terms of the three-phase model, where are we on the three-phase model right now? If we got 12 kilograms in gaseous form at the boiling point. Where exactly on the diagram are we? Yeah, we're on the second plateau, and because that's the boiling temperature. And right at this far right corner here, that represents all gas because it's part of the gas line, the gas diagonal, but it's at the boiling point. So this is as cold as the gas can get while still being a gas. And then we're going to remove some energy. Specifically, we're removing 450 joules. Removing energy means what's happening to it. If it's gas at the boiling point and we start removing energy, what sort of transition is that? Right, it's losing bond energy, and presumably that corresponds to this phase change. So let's try writing out something about bond energy. Presumably this is a change in bond energy. So we're losing bond energy. And what's causing that change in bond energy? Would you say there's heat occurring, or is there work occurring, or is this a closed system, or what? Yeah, we're removing 450 joules. I'm assuming that's probably heat. So let's say delta E bond equals heat. And we know that that heat is negative 450 joules because we're losing that energy. We're removing that energy. And what formula could we use for delta E bond? Yeah, delta M times delta H. So we can set delta M delta H equal to negative 450. And we even know delta H, right? Delta H is the 90 joules per kilogram. So how could we solve for delta M since we want to know? And note that this is a little bit of a jump here. We're not the question isn't asking for delta M. The question is asking how much gas remains. But if we can find delta M, that'll at least tell us how much gas changes phase. Yeah, if we just divide both sides by 90, and I would keep the units here. I would specifically say dividing by 90 joules per kilogram. That way on the left side, 90 joules per kilogram cancels itself out. On the right, 450 over 90 is just 5, so negative 5. And what happens to the units of measurement there? If we're taking joules divided by joules per kilogram, yeah, only kilograms remains. Joules cancels out. And you got to be careful with the fractions here. We have 5 divided by 1 over kilograms, because what's left is 1 over kilograms, since joules cancels out, in the denominator. But dividing by 1 over kilograms is the same as multiplying by kilograms over 1. So we are left with just kilograms. The kilograms in the denominator of the denominator flips up to the numerator. So delta M is negative 5 kilograms. What does that suggest? Negative 5 kilograms means what's happening here? Yeah, 5 kilograms turned into liquid. The negative signifies that we're losing 5 kilograms. Specifically, we're losing 5 kilograms of the higher energy state. Because remember, if we're using delta M, delta H without the plus or minus, delta M specifically represents mass of the higher energy state, which in this case is gas, because gas is a higher energy state than liquid. So if delta M for the gas is negative 5 kilograms, then we are losing 5 kilograms of gas. So how much gas is left? Right, 12 kilograms that we started with plus negative 5 kilograms that we lose. So we have 7 kilograms of gas remaining. The other 5 kilograms have turned into liquid. Any questions on that? And one other thing I want to mention about this one, even if you have forgotten the delta E bond equals delta M times delta H formula, it's also possible to work through this one, at least partway, just looking at the units of measurement. If you just take a look at these pieces you have, the 90 joules per kilogram and the 12 kilograms and the 450 joules, and note that we want to know how much, that is, how much mass is left. We know how much energy we're removing. And we should probably call that negative because we're removing it. If you want to convert that into a mass, you want to convert joules to kilograms, think about this in terms of unit conversion. What would you do with these values that you have in order to make the units turn into kilograms? If we have joules, but we want to turn it into kilograms, how would you get rid of joules? Well, there isn't really a both sides here. We're not really looking at an equation at this point. We're just looking at this value. We know we're removing 450 joules. It might help to think of this as a conversion factor sort of thing, that we have joules. Let me move these aside for a moment. We have joules. And if you think of this as a conversion sort of thing, we want to convert this into kilograms, which means we want to get rid of joules and we want to introduce kilograms. If you can find some way to get joules to cancel out and introduce kilograms, which means we're going to need some sort of conversion factor, some sort of relationship between joules and kilograms. Do we have any quantities listed here that include joules and kilograms? Yeah, the heat of vaporization. If you take a look at the units of heat of vaporization, joules per kilogram, that literally just means how many joules of energy it takes to melt or boil, in this case, to vaporize 1 kilogram of the substance. So that means 90 joules of energy is equivalent to 1 kilogram of vaporized green, or in this case, condensed green, because we've got a negative. So we could fill in 90 joules here and then fill in 1 kilogram. 90 joules of energy is equivalent to 1 kilogram of phase change. So if we multiply these together, the joules and joules cancel out in the numerator and denominator, and we're left with kilograms. You can literally think of this almost as a unit conversion. Even though it's not really a unit conversion, we're not converting joules to kilograms because they're not measuring the same thing. It acts almost the same in terms of getting the units to work out right. So if you just multiply negative 450 joules times 1 kilogram per 90 joules, and note that that's exactly what we were doing here. We were taking 450 divided by 90 joules per kilogram. That's exactly what we're doing here. Then we end up with negative 450 over 90 is negative 5. Joules and joules cancel out. We're left with kilograms. So you could think of this as a conversion problem as well, where you are effectively converting an amount of energy into the amount of mass that is changed phase by that energy. You just got to be careful about exactly how you're combining the units of measurement. but it's often possible just by looking at the units of measurement to figure out the right way to combine some certain values. So I would always recommend keeping the units of measurement, always write in the units of measurement. And every time you're asking yourself, should I be multiplying these? Should I be dividing these? Take a look at the units of measurement and see which way of combining them is going to work out to the correct units that you want. That's often a good way to figure out how quantities fit together, even if you can't remember a formula or if you don't have a formula yet. Yeah, go ahead. Did you have a question? Finding mass of the blue one. Which question is that? Yeah, let me pull up question 3. And then if we have time, we can take a look at FNT5 as well. Question 3. This one? So we've got a process of heat entering a substance called blue. We know energy interaction diagram. We have the initial and final states. And I think we wanted to find the mass of this substance. Was that right? So that's what we're trying to find. We want to know, and again, let's make a list. We want to know mass of the blue substance, blue sample. So that's what we want to know. And let's take a look at what we already have, the known information. We have an energy interaction diagram. We have a graph listing initial and final and everything in between. And we want to figure out what the mass is. So do you know of any equations that involve what we know that also include something about the mass of this object? Yeah, we know that bond energy is changing, and we have a formula for E bond. We also know that the temperature is changing and the thermal energy is changing. So we could figure this out from the thermal energy part. So both E thermal and E bond are changing. So we know delta E thermal, which is M times C times delta T, that does involve mass. Do we know how much the thermal energy is changing during this process? Yeah, we can get that from the graph, right? If we look at just the temperature change, we're going from C is the specific heat. Specific heat of the substance. Whereas M times C, this whole thing is the heat capacity of the object. So we could also write this as heat capacity, capital C, times delta T. The difference is little c is the specific heat of the substance, big C is the heat capacity of the object. And heat capacity is mass times specific heat. So these two formulas are just different ways of writing the same thing. However, since we care about the mass, I would say let's include little m here. So mass times specific heat of the substance times delta temperature equals, and can we see from the graph how much energy transfer this is? If we look at just the thermal energy portion, we're going from initial to the phase change temperature. And then eventually we're also going to this final state here. So from initial to the phase change temperature, it looks like that's how much energy. Yeah, we know that that is an increase of 500 joules. We also know the temperature change, right? We're going from negative 100 up to 50. So what's the temperature change there? Or that's not exactly negative 100, maybe negative 80. Kind of difficult here because we don't have the exact value, but let's assume that's negative. Oh, actually we do, right? It's negative 80. So from negative 80 to positive 50, what's the temperature change? Yeah, it's increasing by positive 130 Kelvin or positive 130 degrees Celsius. If we're talking about a delta temperature, they're interchangeable. So we know the temperature change. We know the energy change. Can we use that to solve for the mass? Can we solve for m in this equation? And how would we do that? Yeah, the problem is we don't know the specific heat of the substance. We could solve for the mass in terms of specific heat. We could divide both sides by C, divide both sides by 130. But the problem is we don't know the specific heat. So this approach, using delta E thermal in this case, kind of runs into a dead end because we don't know the specific heat. If we did know the specific heat, like if this was a known substance and we could look it up on a data table, we could look up little c, plug that in, and we've got the mass. But in this case, we don't have enough information to use delta E thermal. So let's put that aside for now and take a look at delta E bond and see if we can go from there. Delta E bond, we know we are liquefying 12 kilograms of the substance. And how much energy does that take? Looks like we're going from 1,000 to what? Yeah, looks like it costs 750 joules of energy to vaporize 12 kilograms. 750 joules of energy vaporizes, or no, liquefies, let's just say melts, 12 kilograms of mass. So we know that much. We know 750 joules of energy melts 12 kilograms of mass. So we could set up a delta M times delta H and maybe solve for delta H. But I think we might be able to, the thing is that it still doesn't tell us the total mass. That just tells us how much energy it takes to melt only 12 kilograms. But take a close look at this graph. If we go 750 joules, we're only going most of the way to this corner. If we went all the way to this corner, what would we be doing? How much energy is that? Yeah, that's 1,000 joules. So if we only apply 750 joules, we're melting 12 kilograms, which is only, what, 3/4 of the way? But if we go all the way to the other corner, how much would you say we're melting? If you go all the way to the corner, yeah, you're melting all of it. All M of it. So the total mass is melted if you apply 1,000 joules. If you only apply 750 joules, though, you're melting only 12 kilograms. But I think we can use the definition of delta H. We usually use delta E bond equals delta M times delta H. If you solve that for delta H, though, what do you get? Yeah, delta E bond divided by delta M, because we'd have to divide both sides by delta mass to figure that out. So you could think of delta H as a ratio. Delta H, the heat of melting or heat of vaporization, is defined as how much energy it costs divided by how much of the mass changes as a result. And we know that delta H is the same whether you're melting some of it or melting all of it. So we could set up this ratio, energy over mass, for the melting part of it. We could say melting part of it, 750 joules of energy divided by 12 kilograms, because 750 joules is enough to melt 12 kilograms. That should equal the ratio if we melt all of it. Melting all of it costs 1,000 joules, and that would melt the entire mass M. So the energy required to melt only 12 kilograms divided by 12 kilograms should equal the energy required to melt the whole thing divided by the whole thing. And that's now an equation we can solve for M. It's a proportionality. And how would you solve that proportionality? We could cross multiply, and that would give us M times 750 joules equals 1,000 times 12, so that'll be 12,000 joules times kilograms. And then what? Yeah, if we divide by 750, I think we end up with 16 kilograms. So that means the total mass would be 16 kilograms. You could also think of it, if you go back to the idea of proportions, you could say this energy that we're actually applying is 3/4 of the total change. Because if you look at this just in terms of tick marks, you got 1, 2, 3 out of 1, 2, 3, 4. So we're adding 3/4 of the amount of energy. Yeah, again, it's a complicated looking setup, but once you get to the proportion, the algebra is pretty straightforward. And I think you can get that proportion a little more easily if you look at it in terms of ratios. The energy we're adding is 3/4 of the energy it takes to melt the whole thing. That means the amount we melted is 3/4 of the total amount. So we could shortcut this by saying that 12 kilograms equals 3/4 of the total mass. And then because it's 3/4 of the amount of energy it would take to melt the whole thing, in other words, 750 is 3/4 of 1,000. So how would you isolate M here? What's the opposite of multiplying by 3/4? Yeah, multiply both sides by the reciprocal, multiply both sides by 4/3. So 4/3 of 12 kilograms is M, and that's just 16 kilograms. So again, the problem as a whole looks pretty complicated, but if you can split it up into smaller pieces, each one of those smaller pieces is a lot more straightforward. Also, now that we have the mass, if we wanted to, we could plug that in to the delta E thermal equation and solve for specific heat. So we could get more information about that substance as well. Any other questions on that one? All right, that's all the time we have for today, but feel free to email me or come into my office hours if you have any other questions, and I will see you next time. You're welcome.